No guess. So basically, this class, if you look at, right, this is pretty much sequential in nature, and your base would be always, if you go to Khan Academy, go to Explore, go to school and college courses. Underneath, you go to pre-calculus. We have started with unit 1. So we have just done one class so far where we talked about composite or composition functions. So we'll continue from where we had left in the last class, and we'll talk about modeling composite functions, and then we'll talk about what is invertible or inversible function, and then look at the graphs and tables around that. Does that sound like a plan?
Yes, sir.
Okay.
Yes, sir.
Wonderful. So everybody remembers what is a composition function or composite function. No doubt about it, right? When you talk about multiple functions together, that's what is composition function or composite functions. Yeah. Just a quick recap. I have a function of x. Let's say if it is x squared plus 5, and I have a function of g which says, let's say 2x minus 9. If somebody says find function of g of x or function of g of x, we know how to derive it. So basically, find out what is function of x, put it here, and then the whole thing becomes your x. So, and I'll tell you why I'm doing a repeat of what I did in the previous class. So here g of x is, if I have to find out function of g of x, then I'll say function of g of x, and in place of g of x I will put this value, which makes it 2x minus 9. Now this is your new x. If you talk about this, so this becomes, wherever you have x in this parent equation, you will replace that with the value that you have inside the bracket. So this is your x squared minus 5 minus 6. So this is just the composition part of it. Now, okay. Now, why we are talking about this thing, which we have talked about it before. This, we just looked at two levels of composition: function of x, function of x and function of g, and we said we saw how if you combine them, what it becomes. Yeah. So it's very joined from two devices. Alright. Now, is that end of it? Answer is no. You have no limits with respect to what level of composition you can have. It is more like a relationship. If I say A is dependent on B, B is dependent on C, and D is A is dependent on B, B is dependent on C, and C is dependent on D. Like I can give this relationship like A is dependent on B, B is dependent on C, and C is dependent on D. What does it mean? A is dependent on B, meaning A is a function of B. A is a function of B. If I say A is dependent on B, meaning A is a function of B. Now I'm saying B is dependent on C. That means B equals, what am I saying? A is dependent on B, B is dependent on C, A is dependent on B. Okay. So yeah, A is dependent on B, as in A is a function of B. Similarly, if I'm saying B is dependent on C, that means B is a function of C. If you have to find out the relationship between A and C, what it will become? That will become A equals function of B, and again we know this B is dependent on C, so I can say function of B. I'll replace this with function of C. So function of C. And if you have next level of dependency, you can just go on adding function after function after function. You guys are getting logged. Your screen is getting locked, so I have to keep on on touching the screen in between. So what I'm trying to say here is the composition doesn't have limits. You can have nth level of dependency, and you can simply go on and use the same technique even if you have, let's say, 5 levels of depth in your function. It could be like function of a function of let's say function of a, let's say. So what we are seeing here is something that is coming from this function as an output is becoming an input to this function, and whatever comes as a total outcome or output from this whole thing becomes an input to this one. So you can have n level of depth when it comes to composition of function. It's not limited to only 2. And when you have multiple relationships, multiple depths, that is all about modeling a composite function. I know I've been talking non-stop. Let me take a pause. Anything that I made complicated for you guys so far?
Yes, sir.
What did I make complicated? The question was, did I make anything complicated?
Yeah. Yeah, so wait. Does that say F of wait, can you explain what it says again? It's
Yes.
kind of confusing.
So what I'm saying is, let me do that in a reverse way. Okay, that will make it probably look easier. If I have, let's say, something as a function of a, okay, let's say this is my weight. Okay, so my weight is a function of how much I eat. Okay, that's fine. So this is my, so let's say if my weight is a function of how much I eat, I will say this as this. Weight is function of how much I eat. This is the amount of eating I'm having every day. Okay, that's fine. Now
Yeah.
I'm saying the 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 size of my pants would be a function of my weight. I know this might not be right, a good decent example, but just bear with it. Okay, this is the only option that is coming to my mind right now. So meaning how big my trouser would be a function of how much is my weight. Correct? If I get very fat, I would need bigger trouser. Correct? So my weight is a function of how much I eat. My size of the trouser is a function of my weight. Can I say so? Yeah?
Yeah.
Now, depending on how bulky I get, my frequency of visits to the doctor, so my frequency, if I say frequency as in F, F is confusing. Let's say my frequency of visiting a doctor, okay? How many times I will visit the doctor in a month is a function of how bulky I get, right? I will say the doctor's visit is a function of the size of my pant or trouser. Now you see this. This is like a story, okay? I'm stitching things one after another. My weight is a function of how much I eat. The size of my trouser is a function of what my weight is. And the number of doctor's visit is a function of what is the size of my trouser. Meaning, if I get very bulky, I will make more frequent visits to the doctor. Now, if somebody says, what is the relationship between the number of visits versus how much I eat? What it will become? So let's go step by step. If I know that this, okay, let's look at this. So W equals function of A, meaning my weight is a function of how much I'm eating. If I have to find out the size of my trouser against my daily consumption of food, then I see that okay, daily consumption of food leads to weight size of trouser. So if I have to relate size of the trouser against this one, that means I have to go two levels from here to here. Yeah. So function of size of trouser is function of weight, and now this function of this weight is a function of this. So is in place of W, I'll replace that with this thing because we see this. So let me do it. So function, see, size of my trouser is function of weight. So I can do this, which is written here. I just copy pasted. Now I know that my W is equals this one. So I'll replace W with whatever I see from the previous equation. So right now what you see is the size of my trouser is related with how much I am eating every day. Is this relatable so far? Are you able to follow me?
Yes.
Now, I am not happy with what we have done so far. I want to go one more level because I know my doctor's visit, number of my doctor's visit in a month is a function of this. Can I relate my doctor's visit with this one? With how much I am eating? See, if you keep eating more, you might end up seeing the doctors more. Yeah? Or vice versa also. If you don't eat, you will see the doctor more again. But again, with respect to this equation that you see here, now if I try finding out D, my state equation is D or the number of doctors with a state function of S, meaning the size of my trouser. Now, I know that size of my trouser is this. So I will replace this with function of W. Okay. Now, again, W equals this. Function equals, so wherever I have W, I'll replace W with function of A. So here, if you see, I mean, first of all, let me just check. Are you guys able to relate my daily consumption of food with the doctor's visit?
Yes, sir.
Confusing? Not confusing?
I get it.
You get
It
it?
makes sense.
It makes sense. How about you, Chris, Dave, Sally?
Yes, sir, it makes sense.
Makes sense.
Yes, sir.
So this is not complicated. It's just about how do you peel off the onions. Here, when you look at this, it's a reverse of peeling of the onion, right? We are putting layer after layer after layer. And in actual sense, this is nothing but relating things which are dependent on each other. While all that I told so far might look a cryptic speech, but then it is nothing but just substituting values. Simple. My weight is a function of how much I eat. Okay, so weight is function of how much I eat. Now, and my size of my trouser is function of my weight. How bulky I am, I would need bigger or smaller trouser. Now, so size of the trouser is function of weight. We know that weight is a function of this. So instead of W, I just put this value. So this becomes, size of my trouser becomes function of this. In place of W, I have. So there are two functions. So we are going two levels, you have two functions. You go to third level, you have third function. See, you have three F's written here. Yeah. So this is called modeling of composite functions or composition function, which essentially means how you relate different things or different functions or different relatable variables to come up with multiple levels of function, and that is simply called modeling of functions or modeling of composite functions, if I can say so. Everybody with me? Not with me?
With you, sir.
Okay, good. Now let's look at a practical example. So that way you can relate. Now, who all knows laws of motion? Everybody?
Law of motion.
Laws of motion?
Like Newton's laws?
Yep.
Yeah, I remember.
I remember. Okay. No, so anyways, I mean, the objective is not to kind of bother you with that, but I'm just putting it on the table, on the screen, and then you don't have to memorize that. If you know it, wonderful. If you don't, that is outside the purview of this class. I will not try going there. But then there are two formulas that we know from Newton's law of motion. The third law of motion says force equals to mass into acceleration. Sorry, this is the second law of motion. Anyway, don't bother about first, second, or third law. One, Newton's law of motion says force equals mass times acceleration. And when you get a question on this one, you will get it like this. They'll say, okay, how much force you apply derives the acceleration based on what is the mass of the object. Okay. Now, other law of motion tells us that the new velocity is equals the original velocity plus acceleration acceleration times the time with that acceleration. So let's not try decoding these two this thing, but the simple thing here is force that you apply for any acceleration will be equal for generating any acceleration will be a multiple of mass and the acceleration needed, and then the velocity will be the new velocity would be a function of this. So from this you can say A equals V minus U by T. So you have two things here. Now if I put this value of A here, so you have two functions given. See here, this is one function. This is one function where force equals this is one function, example of a function. This is second function where acceleration equals new velocity minus original velocity divided by time. Okay. Now there are two functions now. If you end up replacing this A, meaning put it here, then what it becomes? Mass times V minus U by T. So here what is happening is we are kind of making this a composite function. See, this A is a separate function. We are plugging the value of A here, right? Like we did, there is a function x equals to 4x plus 3, and then function g equals 2x square. Same thing, function, this is one function, this is my output which equals this, and the output that is coming from other function becomes an input here, right? This is essentially a classic example of composite function or composition functions. So if you have to find out, if you are given these two functions, and you have to find out the force based on mass, velocity and time, you can use that, correct? So and let's say if again let's say time is a function of something else, then you will plug the value of t here and calculate it. So now if you have a problem like this to solve, where you are given one relationship or one function like this, other function like this, and you have to find out the value of this based on these 4 variables, you can relate them, because this function gets plugged in here, so this becomes composition function. So likewise, if you have 2 or 3 or 4 levels of depth, you will see that you have to just keep on replacing the values which is coming as an output from another function to make it a composition function. And that brings me to a point where I want to stop and check. Are you guys with me?
Yes, sir.
Yes, sir.
Right. And don't be shy. If I'm making it complicated, you have all rights to say, sir, I didn't understand. That's fine. That's my job. Yeah. So now, with whatever concept I talked about, same Khan Academy you guys will go to. Open Unit 1, look at composite function, no, modeling composite functions, and there will be unit test around that one, which I would want you guys to do. And the unit test will actually help you as ascertain that whatever we are learning, are we learning it enough to be able to solve those? And if you get stuck anywhere conceptually, that's an opportunity for me where you'll come back to me saying, sir, when I was trying to solve this problem, whatever you taught, that was probably not enough, or maybe I missed some concepts. Can you solve this problem? Okay. So for you all, right, this is my senior most group of kids. Okay. I would want you guys to kind of collaborate a little more with each other. Whenever you come across a problem that you're not able to solve based on what we have learned, you put that question in the group. Say, okay, this is one problem that I'm trying to solve. I'm getting stuck. Is anybody willing to give it a try? If nobody tries, your teacher is anyways there. He is obligated to solve it, but when you share among yourselves also, that becomes an opportunity for you all to practice. Okay. Now, shall we move on? Is that a good idea?
Yes, sir.
Okay. Okay. Now, let's talk about what is an invertible function. But before we talk about invertible function, let's quickly touch upon what do we mean by domain and range. Who all knows it? And who all wants to know it?
Domain is all possible x values and range of all possible y values.
Okay. That's one definition. Anybody else wants to redefine it in a different way? Yes, Arya.
Domain is like the smallest x value and the largest x value on one like coordinate, and then the range is the smallest y value and the largest y value.
Okay. I got two definitions. Somewhat close. If anybody wants to give it a try, let me know. Otherwise, I will continue. Okay. Simple terms. When you say domain is all your inputs and range is all your outputs for a function. Very simple layman's definition. Okay. So if you look at these two sets, let's say I have a function of x such that my inputs are, let me put it like a table here. I have a function x where this is my x value and this is my corresponding y value. Let's say when x equals to function of x equals, whatever equation it is, let's say if it is 2x minus 7 is my function. Okay. When x equals 2, this becomes 4 minus 7 minus 3. When x equals to, let's say 4, it becomes 4 to the 8 minus 7, 1. When x becomes minus 2, it becomes minus 4 minus 7 minus 11. When x becomes, let's say 0, my function of x, this output becomes minus 7. So here what you see is, these are the 4 possible inputs that we have given. Okay? And these are corresponding outputs. So all the inputs for a function are the possible inputs for a function, right? At times you might have a situation where you cannot give, beyond a certain range. Okay? So let's assume that all the possible inputs that you can give to a function, that is called your domain. Okay? And all the potential output that you will get, that is called your range. So if I put it here in a different way, 2, 4, minus 2, 0, this is my list of domain. This is, I'll not call it list of domain, I just said domain, that simply means these are my inputs to this function. And if I call this as range, this is going to be my list of outputs. Now let's say minus 3, minus 7, minus 11, 1. These are my 4 outputs. Okay. So this is called domain and this is called range. No doubt so far?
No.
Okay. Now you can map it. When my input is 2, my output is minus 3. So this is connected to this. When my input is 4, my output is 1. So this is connected to this. Okay. When my input is minus 2, my output is minus 11. This is connected to this. When my input is 0, my output is minus 7. So this is connected to 1, minus 7. So this is my domain, this is my range. This is just another representation. So far so good? Domain range, no problem?
Yes, sir.
Now let's add some more fun to it. Because if we don't add fun, it becomes funny. Let's add one more input. I will say when my input is 4. Sorry, when my input is 6. And forget about this function. This is some other function, okay? Some other function. My input is 6, then my output is minus 3. It can happen, okay, depending on how the function is constructed. Right now, you're not worrying about the function, you're just looking at this table where you have certain values as input or domain and the corresponding output. Yeah?
Yes, sir.
Now, what will I do? I will make this ellipse a little bit bigger. I'll add another input here. And then this guy relates to this one. So for this story is fitting well, right? Yeah? No, nothing complicated so far.
Nothing up. Yes, sir.
Now, let's again reverse what we did. I'm just taking it out for a little bit. And you guys will assume that this doesn't exist. So between the previous drawing and what we added, only thing that you saw was one extra input was added and this was relating to the same, one of the existing outputs. So we did not have, we had 5 inputs and we had only 4 outputs. Yeah, because there were 2 inputs relating to one output, correct? Or one of the range. Here, and there was a reason why I deleted the last record that I added, okay? Now, here in this case, what you see, for every value of input, there is only one corresponding output. Meaning, for every domain value, there is a corresponding range value. Every domain value, there is a corresponding range value. Every domain value, there is a corresponding range value. Here, now if you inverse it or think in a different way, if I am saying this is my function x scenario, okay? There is something called inversible function minus x. Do you know what it means? Does anybody know what an inversible function means?
Isn't it where the x and y values are flipped? Like, you have to set the equation equal to x.
Right. So that was a very, what do you call, data-driven example. My approach is I always start with a layman's definition and then we'll relate that with maths. Okay, so now inversible function, if you look at it conceptually, this is my domain, this is my range. This is my input, this is my output. And inverse function is, it flips the whole concept. It says here for this input you have an output. Inverse of this function would be where your output becomes input, input becomes output. So for function of x, this is my input, this is my output. For inverse of function of x, this becomes my input and this becomes my output. of silence. Everybody with me?
Yes, sir.
Okay, one more time. So, simple function, when you talk about a normal function, you have a domain, you have a corresponding range. Every value in the domain maps to one value in the range. This is my normal scenario. Now, when you talk about inverse of the function, that is when you say, now I will flip the story upside down. Meaning, whatever was my output becomes my input, and every output has a so whatever was my output before becomes my input, and for those values, the output will be matching with the corresponding, the old input values. So basically, you were looking at it from this side, now you have changed your plan, you have come to this side and you're looking at this way. So this side it is function. When I moved by 180 degree, this is my new function, and this new function is called inverse function. Yeah? Is this relatable?
No, sir.
Yes, sir.
So now coming back to what Ishwari said. Ishwari said, my x value becomes y value, y value becomes x value. That is the mathematical way of looking at it. So here, look at this. In this function, what was the case? Y is a function of x. So here, if this is my y, this was function of x. Now when I am going here, my x becomes function of y. Okay? From this side, my x value becomes my function of y. Correct? And this, instead of saying x is a function of y, we say this is a inverse function of x. Yep. Nobody is wanting to hear me again, right? For this one? Okay. I'm just trying to confirm. Everybody is clear with this, right?
Yes.
Yes, sir.
Okay, now let's go back to the mysterious thing that I did a little while ago. What did I do? I added one more column here and I said my input is 6. So in this case, when you have one value for x, there is a corresponding value of y, one value of x, corresponding value of y, and this, when you look at it from this side, this is inverse function. Now, as long as you have one-to-one mapping between input and output, and when you